So this is problem set 5, right? And I made some changes to send it out. Revised
Version. Okay, the first one is simple. 9.2. So we have a force drive on the mass of a simple harmonic oscillator here. So this is the chapter 1, right? There's a force exerted on this mass. And then now we're adding this semi-infinite string. So you remember, again, like we're doing a lot in this class, from an impedance point of view, this acts like a resistance because there's no waves coming back. It's just a pure resistance. And we know what that resistance is. The impedance is a resistance in this case. It's rho L. I can't believe I did that. Okay, we'll correct that. So what we have here, the nice way to look at this is from an equivalent circuit point of view. Every element here has the same velocity mechanically, right? The spring, this velocity, same here, the mass, the resistance, and the end of the spring. They all have the same velocity. So all these impedances are going to have to, for the electrical circuit, equivalent circuit, are going to have to be in series because we have to have the same current through each element. So you'll notice this, again, this is just like, except for this, just short this out. This was chapter 1. And now because of the string, we see a pure resistance of rho C. If the string were terminated here, what would we have here? Well, I can't remember what it is. We're going to see it many times in this problem set. We calculated the impedance of a string driven at one end and terminated with zero displacement at another end. So you would put that in there. And where was and so this is a mistake. This should be, I don't know, I was thinking an LC circuit. I don't know what's going on here, but this is rho sub L times C, the speed of waves, right? Crazy. Pardon me?
When you talk about the velocity of a spring, you mean like the difference in the bottom and top part, which is
yes. And in this case, because there's no velocity down here, it's really. I picked this up, I think, in the transducers course, the textbook we use, which is written here. It's technically it's the velocity difference that's important here, but it's just so much easier to say the velocity. But technically you're right. It's all that's important for this spring, here, is the difference of the two velocities there. That's what gives you a compression or expansion, and similarly for the dash pod. Okay, any questions about that one? Okay, the next one is, the next one, 993. String is stretched between two supports. It's driven by a force located at its midpoint. So we haven't done this before, right? But you're going to see that it's easy from the results that we have. So it's driven here at the midpoint. There's a force. What is the mechanical impedance at the midpoint? Okay, so what we see here, driving it here, we see two impedances. There's going to be impedance due to the left part of the string here and an impedance due to the right part of the spring. So if you look back, it's in the textbook and we derived it. For the impedances just add here, as we proved in class. The impedance seen by this is going to be the sum of these two impedances because the velocity is the same and the two forces add. That's basically the bottom line there. So we calculated, as I just mentioned in the previous problem, we calculated the impedance seen by the drive here for a fixed string here of length L. So we just take that result and let L go to L over 2. So this is what we derived in class. We let L go to L over 2, and then we double it because it's the same impedance on either side. Symmetrical problem here. So that's the input mechanical impedance. We're asked to find the displacement at x equals 0. Okay. Incidentally, all of these problems are steady state motion, right? I've sort of stopped saying it. We're interested in the steady state here. So even though you'll see that there's no resistance in our model here, you want to assume a little tiny bit of some kind of resistance so it can reach steady state technically, right? Okay, so how do we find the displacement here? Well, that's one of the major uses of impedance. Once we know the impedance, remember the impedance, complex force over the complex velocity, and because we are interested in displacement here, the velocity is the time derivative of the displacement, and that just brings down an I omega, the time derivative. So we replace the velocity with this. This is the quantity that we're interested in. We just solve for this because we know everything else. We know the impedance. That's one of the big utilities and advantages of using impedance. So it's going to be the force divided by the impedance with this factor of I omega here. And now we just substitute in what our impedance is. I've done that here. Okay, then we look for simplification. I times I is -1, so I did a little bit of simplification here. And now what can we do with this? Well, normally what people do is they put the trigonometric function upstairs here. The inverse of the 1 over the cotangent is the tangent. So we get this. And that's about it. I see one more thing that can be done. Oh yeah, we're going to have to do it too. I guess the textbook gives us, do they give us a certain expression here that we're headed towards? Is that right? You're going to make me read it? Okay. Yeah, it tells us, okay, so we don't have the expression that they gave us, but you can see, what's omega times c? Well, what's omega? Omega is equal to ck, right? So we're going to get rid of omega in terms of k. Omega is equal to ck. There it is. And also we're going to use the fact that c is the square root of the tension over the density, the speed of waves. So then we achieve the expression that they want. This is equivalent to what they're asking. So that's the displacement, and often we care about the amplitude, and you just kill the e to the I omega t, and you have the amplitude. Okay, so there's a part C here. Oh, okay. Now, what's the amplitude here? Now you have to calculate it. There's no way, we're doing this in general. This is algebraic. We're not specifying any values here. So you have to do it. So how do we do that? Well, I don't know if you remember, but I told you that the impedance tells you nearly everything you need to know about the system. Sometimes you have to do a little bit of extra work. Do you guys remember me telling you that? Well, we're going to see that again and again in this problem set. So how does the impedance help us? Well, it gave us, we know what's going on here, but how do we find out what's going on here? Well, there's a little step we need to make, all right? And it's this. We know we're going to have a standing wave here. A pure standing wave, because there's well, if you like, you can imagine a wave traveling this way. When it reflects off here, it has to have the same amplitude because of energy conservation. So you know, and similarly over here. So you know we're going to get a standing wave with nodes, pure nodes. So what we do in a case like this is this little extra step that I was talking about last week or the week before, I can't remember. We know, let's focus on the right string, the right half here. Okay, so for positive x. We know it has to be a standing wave, so it's going to have an e to the I omega t that's isolated, that multiplies everything, because that's mathematically a representation of a standing wave. It's just, okay, what about the spatial part? Well, this has to satisfy the wave equation. So it's going to have to be sinusoidal. It's going to have a kx in it, and then we need to meet the boundary condition here. So at x equals L over 2, we have to have 0 for all time. So you can see that this does it. So what we do, and this, I know this probably seems difficult for you right now, we just write this down. And after you do it a few times, it's pretty simple. Right now, it's probably, you're thinking, oh, I have to remember this? Well, it's really not that hard. Okay, we got to have a solution to the wave equation. It's got to be sinusoidal. You know that in space here, and it's, you know, we know it's sinusoidal in time because of this, but it's got to be sinusoidal in space. We have to have a nice standing wave there. And we've got to meet that boundary condition, and that does it. Now you can switch these if you want. It doesn't make any difference. And the interesting thing here is we don't know what this amplitude is. Okay, that's what we're after, right? I think that's what we're after. Is that what we're after? The amplitude at L over 4. All right. So we're going to do this a lot in this problem set, and later on in course 2. This is the easiest way to do it. Okay, so what we want to do is to make contact with what we know. We're going to evaluate this at x equals 0. At x equals 0, we know we have to get this. So that's the connection here. Once we've written this down, this general expression, which is valid all along here, we take our solution at x equals 0, and that's going to allow us to determine this a. So we just set x equals 0 here, and set the resultant expression equal to this, cancel the e to the I omega t's, and solve for the amplitude. And when you do that, you get this. Okay? So now, once we've got the amplitude, we can put it back into here, and now we have the displacement. Now we have the displacement for the whole right side of the string. It's similar for the left side. And once we have that, we can evaluate it, okay, for L over 2. Excuse me, L over 4. Halfway between the driven point and the termination point. So when we do that, we just get this, this becomes the sine of KL over 4, and we recognize the amplitude here. The amplitude is everything multiplying the e to the I omega t, right? All of this. So that's the result. That's the amplitude at, I should have written L over 4. This is the amplitude at L over 4. Kind of weird. With that, I don't know. Weird. Okay. I see some looks that don't look great. So I think this is probably causing a problem, but we're going to be doing it again in this problem set, and then later on too. Okay, next is 9.4. So we're given specific values here. We have a string with certain density, linear density, tension, rigid support, a driver, length of the string. Okay, fine. When the driving frequency has a certain value, the nodes are spaced 10 centimeters or 0.1 meter apart, and the maximum amplitude. Okay, so the first thing I need to tell you is this is an example, not a great example, of what's called an inverse problem. How many of you have heard of inverse problems before? Yeah, the idea here is that normally we know the force, right? But in this problem, we're going to work backwards and get the force from the response. So it's not a great inverse problem. More interesting type inverse problems, and this can occur, for example, with sound in the ocean. By looking at this wave here, we can figure out the density or something like that. Usually we're given the mass per unit length, right? So, but by taking data, we can work backwards and find out the parameters of the system. That's basically an inverse problem. And some inverse problems are extremely hard to solve. Some of them are not unique. You don't have enough. Sometimes you might think you have enough information, but you don't. So and then this acoustic sequence, we will encounter a few of those. And when you go on to get into ocean acoustics, which I don't know anything about, there may be more. I don't know. But it's just good because this comes up, not just in acoustics, it comes up in all kinds of areas of physics and engineering. You know, the classic radar or acoustics problem is, given some signal that's bouncing off something, can you identify what it's bouncing off of? That's the classic military application of an inverse problem. Usually we know that, you know, a structure that's, we solve for a wave coming and bouncing off. We solve for the scattered field, okay? Well, in this, the idea here is that you're measuring that and you want to figure out what the scatter is. That's the classic inverse problem. Okay, so the first thing you want to do, you do the simple thing first here. We know that we're going to have a standing wave with nice nodes, and we're told the distance between the nodes here. So that means we can get the wavelength. We just double that distance. So we know the wavelength, and from that, we can get the frequency. They tell us that we're asked to find the frequency. So we just get it from this simple relationship here that the wave speed is the distance divided by the time, 1 over the frequency. So we know the speed of waves because we know the tension and the density, so we can find it. It's 22.4 meters per second. So I just plug the numbers in, and it's 112 hertz. Okay, so that's the easy part. This way. What about this way? We want to find, what we're asked to find here is the drive amplitude. Okay, so I have a funny feeling. Here's what I'm missing. We're given that the information is that the amplitude is 2 centimeters. Now, when we talk about a standing wave, when we say the amplitude is 2 centimeters, that's of course the maximum amplitude. You need to make sure you keep this straight because we're going to have there's going to be an amplitude right here. Do you think it's going to be 2 centimeters? I don't think so. Okay, right? The amplitude of a wave is of course the maximum amplitude, and in fact KFCS will often just insert the word maximum in there, even though it's not really necessary. When we talk about an amplitude of a wave, it is the maximum, but they do that so that there's no confusion. For example, it's not going to be, we'll go through it, you'll see, we'll get the amplitude here, and we won't be done. We won't be done with the problem, as you'll see. Okay, so here we go. How do we handle this? You know, one word, right? Impedance. So the input impedance here, this is a forced, fixed string. Here's the input impedance that we derived in class, and it's going to equal the complex force divided by the complex velocity. We care about displacement here, so just like before in the previous problem, I'm going to go to I omega y, the derivative of y to get the velocity, particle velocity. We can solve this for the displacement, and we get this. Okay, now here's the warning here. You look at everything multiplying e to, there's an amplitude. In the steady state, you know there's going to be an amplitude here, right? But you don't want to set that equal to the 2 centimeters. That's what this is about right here. Okay. And in general, not going to be the maximum amplitude of the wave. Now, how do we find? We need to get away from the driving point here. We need knowledge of the waveform. It's just like the problem we just previously encountered here. So again, to do that, however you want to do it, but this is the quickest and I think easiest way, is we know it has to be a standing wave. We know it has to solve the wave equation. So here we are. This is just like very similar to what we had before. Maybe a factor of 2 difference somewhere. Very similar to what we had before. We know that that string has to have an e to the I omega t for the standing wave, and it's got to vary sinusoidally, and it's got to be 0. We've got to get 0 here at the termination point. That's a boundary condition. So we set this equal, you see I've written that here, we set this equal to our previous, see, what are we doing here? Sorry. So what are we gonna do with this? Well, to evaluate this, we know, I almost said amplitude, and it is correct. We know what the amplitude is at x equals 0. It's not the amplitude of the wave, but we know that amplitude, right? So we set x equals 0 here, and we get this, and then we just pick out the amplitude of the wave at x equals 0, which is all this right here, except for the e to, take the modulus here, get rid of the e to the I omega t. And that allows us to determine this a. This a is the amplitude of the wave. It's multiplying the sinusoid here, it's the amplitude of the wave, the maximum amplitude of the wave. So we can solve for it, and we get an expression. And you'll notice it's different than the amplitude at, you can check that, it's different at the amplitude, it's less. This is greater than the amplitude at x equals 0. Finally, so this is the sort of the inverse problem here. We're told this, so we can solve for, we found the frequency of the drive, we're not going to find the amplitude of the drive. I can easily solve for this. And we're going to beat on this a little bit. Substitute in what A is. Wait. Yeah. Right. So we know all of these quantities. We're told the amplitude of the wave. We know K, we know L. We're told the tension, we know the wavelength. So we can just plug in the numbers at this point, and we get about a Newton. That's the amplitude. Looks like they were shooting for a Newton. I don't know. Okay. Get the idea? There's going to be more of this kind of as impedance type calculation. Any questions? Okay, so, you may wonder why this is white. And I don't know, I think I lost the original yellow, but I had a copy. I don't know, it's happened before. But it looks okay. So this is 9.5, the bottom of the page in the book here. So we have a forced fixed string. This is the usual, simple situation where we have a massless ring and a frictionless pole, right? It's a nice model system here. And we're going to now, the point of this problem is to investigate not a force drive, a different type of drive. I've talked in a lecture before about a displacement drive. That's where you have a certain frequency and the amplitude of the displacement is specified. So the physical idea there is that, like when I drove that long spring, the idea there is that as you change the frequency, the displacement amplitude remains the same, not the force. So that's not a force drive, we call it a displacement drive, because that's what's specified. So we're going to do a similar thing here, but it's going to be velocity. And we'll talk about the displacement drive next, but we're going to do so this is often called a velocity drive. In fact, they might have called it that. They're a little bit more careful with English, but we usually just call it a velocity drive. Now, so we're going to go for maximum response here. Okay, that's what we're interested in. What most people call resonance, not KFCS, and I'll explain that to you. But everybody else in the world usually thinks of resonance as maximum amplitude, okay? Or close to it, as we've seen for an oscillator. Dissipation can make it a little bit different. So how do we approach this? To solve, the simplest way to do this is to, first of all, we got to have the wave equation here. You know you're going to have a standing wave because this we're going to get all the energy going in is going to be coming out, so we know we're going to get a standing wave. So we do the same thing we've been doing. This is the third time, I think. We know that it has to be sinusoidal in space. It's got to have an e to I omega t here because it's a standing wave. And there'll be some, in general, complex coefficient, some amplitude. This is our complex amplitude right here. So this is the displacement. We have a velocity drive, so to make contact to make contact with the x equals 0 point here, which is just a special case. We can let x be anything here between 0 and L. To do that, we need to take the time derivative here to get the velocity of an element, any element of the string. So it just brings down an I omega. So here's the velocity of any element of the string. We evaluate this at x equals 0. Okay, and we have to get, at x equals 0, we have to get that. That's the driving condition. That's what the drive is doing. The drive is causing a certain velocity amplitude at the x equals 0 point. So by setting x equals 0 here and setting the result equal to this, we can determine the complex amplitude. We just solve for this and we get that. Now we can take the complex amplitude, substitute it back in here, and now we know everything, right? Now we know everything we need to know about the solution. And we can look for the resonances, or as KFCS would say, the maximum amplitudes. So we have this. This is a common structure that occurs here, and you'll notice how it occurs. Remember how it came about. What happens when I let x go to 0? This cancels, right? And we get the velocity amplitude divided by I omega, which is the displacement amplitude. So you see this a lot in standing wave analyses. All right, so we have no dissipation in our model. You know we're going to have infinite response on resonance because we have nothing to limit the growth. And sure enough, it's going to be where the sign goes to 0. So there's an infinite number of these. It's when KL is equal to n pi. So here's what they look like. We've seen this kind of thing before. This is like the spring, very much like the spring, which you naturally drive with a displacement drive. Here's the fundamental. It's a half wavelength. The second mode is 1 wavelength, etc. So we would summarize this by saying, oh, and these have, incidentally, they have infinite response, right? Because this is going to be infinite. So I've just drawn them like this, but this is really infinitely up there, right? And infinitely down here. So these are the maximum responses here are infinite, and they correspond to a fixed string. So the way we would say this now, after yesterday's lecture, is they correspond to the normal modes of a fixed string. The normal modes being the modes of the system itself without dissipation and without drive. We saw that, right? This can be the normals. That's the normal way of, that's the usual way of saying this. The resonances here correspond to the normal modes of a fixed string. Is this what we got for the force drive? We considered the system with a force drive. Remember what happened there? It's this, right? So we need to reconcile the two. So before we do that, there's a part B here. The part B is for a displacement drive. So that's like the string that I keep long spring that I keep talking about. In this case, at the input point, there's going to be some amplitude. I'm going to call this Y0 because you'll see why in a moment. I don't want to call it A. I want to use A for acceleration here. So the displacement drive, as you change the frequency, has a fixed constant displacement, which we're going to call Y0. You can go through, it's very similar to this calculation right here. It's very similar. In fact, you can just look through this calculation, and instead of doing the velocity drive, you can imagine the displacement drive. There's just a factor of I omega difference. It's very easy. I'm just going to give you the result. The result is this. And you can see, does it work at x equals 0? Yeah, at x equals 0, we have to have the displacement of the drive, which is Y0. And Now it has 2 bars on it. I don't know how that happened, okay? Sorry. So sometimes I and other people do this to distinguish it between a lowercase y. We put these bars here. That's supposed to mean it's uppercase, okay? So I should have done it here. Now, I don't think the textbook asks this, but I went ahead and did it. For the acceleration, we can have an acceleration drive. Now we have the amplitude of the acceleration is fixed as you sweep or change frequency. Very similar calculation, and you get this. So for the displacement. So you can see here that, you know, the displacement amplitude, because it's simple harmonic motion, is going to be the acceleration amplitude divided by omega squared. So it's very reasonable here. It's 180 degrees out of phase. So all of these drives here, the displacement, we started off with the velocity drive. This is the displacement drive. This is the result of the acceleration drive. They all have maximum amplitude when KL is equal to an integral number multiple of pi. So they're all going to, the resonances are all going to correspond to the normal modes of a fixed string. Okay. So here's what we found. Here's what we found in lecture. It's also in the book when you have a force drive. And now we get the maximums by setting the cosine of KL equal to 0. And we followed that through, and what it corresponds to are the normal modes of a free fixed string. This is the first one, quarter wavelength. This is the next one. It's got 3/4 of a wavelength in there, etc. So there's a difference. And when we hit upon this earlier in lecture, and I just commented to you that I made the comment, I think, that you have to be careful that the resonances depend upon the type of the drive, whether it's a velocity drive or a force drive. All right? Now, that's not how KFCS would say it. If you look at this problem here, part D, okay? This is interesting. There's just no equations, just all words. If you look at part D, does mechanical resonance always coincide with maximum amplitude of the motion? That's not the kind of language I've been using. I've been saying, you know, this is resonance here. Maximum amplitude is resonance. Most people treat resonance and maximum amplitude, you know, they're synonymous. But not KFCS, okay? To them, they're wedded to this force drive, right? And the resonance corresponds to the vanishing of the reactance. That's like a commandment, okay? In this Bible of impedance that we're dealing with here. Okay, so to them, if you look back at anybody look at the answer in the, probably haven't gotten to it yet, but if you can look at the answer in the back of the book, it's an odd number problem. So does mechanical resonance always coincide with maximum amplitude? And they say no. Okay? What they've done is they sort of painted themselves into a corner. Is there a foreign expression? We have a lot of foreign students here. It's probably universal. So like in Korea, what do they have? You painted yourself into a corner? Okay, not in Korea. Greece. Okay, well, we have to change this. Taiwan?
How do you paint a room in Taiwan?
You are from Taiwan?
Yes.
Okay, but you don't have paint in the corner. Oh, so maybe it's an American expression. Okay, so, well, I don't know. Okay, you guys work it out amongst yourselves. You do that well, okay. they've by insisting upon a force drive and stating that the reactance has to vanish, you know, they're forcing a force drive here. That's not the only kind of drive out there. So I was thinking about this, and here's a way that they can be fixed. Now, I'm not sure if this is what people do, but I think what I'm about to tell you, I think is the natural thing to do here. When we have a displacement drive, Oh, I've told you that this is the first time we talked about this. I'm pretty sure that I stated that the whole idea of impedance is complex drive. Note that I'm not saying force. I'm leaving it unspecified. Complex drive. And what do I put down here? Do I put the complex velocity? No, I put response, right. And then I told you that we need to appropriately choose the response. Well, it holds, as far as I'm concerned, the way out of this thing with, maximum response here not corresponding to resonance is that we have to change this too. So if I have the way I would view this is when we have a velocity drive, this is going to be the complex velocity drive. And this could be the whatever response you want. It could be the velocity of the response. And that's kind of curious because then the impedance becomes dimensionless. That seems very strange to me, but this is the way to get around it. If you do this, then you're going to find that everything's fine. The vanishing of the reactive part is going to give you which is resonance, is going to give you a big response. Everything will be fine. So it's not going to be a big deal for this course because we almost always concentrate on force drives, especially when we do acoustics. Although in the first lab next quarter, we're going to have a tube driven by a loudspeaker, and it's modeled by a displacement drive. So it does come up. It does come up. And to KFCS, they have a sort of a different attitude about this. So anyway, this is one way around it. Now, another thing I realized. If you do get away from a force here, in your equivalence, if you have an equivalent circuit, it won't be voltage. If you have a velocity drive, suppose we have a velocity drive here, okay? How are we going to model that in the equivalent electrical circuit? It's going to be a current source. There's nothing wrong with that. Current source exists, and equivalent circuit is all in our heads anyway, right? It's just for us to more easily understand the system and deal quantitatively with it. So, and a displacement will be a charge source. Okay, that's okay. Those exist, I think. But it's not going to be a big deal. But I just wanted to point it out. I signed this problem just to reinforce what we talked about in lecture. But you have to be careful about the nature of the drive. When you're going to get different types of resonances, what I would call maximum responses. What I would call resonances, and I'm all confused. KFCS would call maximum responses, but most people would say, oh, they're resonances. The system's resonating. You got the big amplitude. Okay, are there any questions? I doubt any questions about that? Okay. All right, so there's one more. So we've done, similar problems here. So now we're going to drive at the midpoint. Should be moved over a little bit to the right there. And now we have, we did this previous problem. Okay, so this is very much like this problem, except now we're going to mix the boundary conditions. It's going to be fixed, free, I think. So that changes. We have a different system now. So this is 9.7. This is done, no values here, it's just algebraic, right? And I don't think I've said this before, but an advantage of an algebraic type problem like this, where you just have these symbols, is you can then, once you've got a solution, you can plug in any values you want to, right? And in particular, you can check it in limiting special cases. So that's one of the advantages of dealing algebraically with a system, just dealing with symbols here. Another is it can be easier to deal with mathematically. It doesn't get so cluttered. But it can work the other way too. It can be that when you do something algebraically, it gets really messy, and it's easier just to plug the numbers in. So what you do is you learn by experience. If you're having a tough time with the symbols algebraically, and it's a numerical problem, and you're after a numerical answer at the end, maybe it's good just to go to numbers. And I will usually tell you in a quiz, right? I'll expect you to know this, but and I know cases where it is easier with dealing with all this impedance stuff. If you're interested ultimately in just a numerical answer, it's often better to just plug the numbers in right from the beginning. Okay, so here's the problem. We're driving the string here, and I want to point out here that we have you look at a point here in the string. It has differential mass, vanishingly small mass, right? And it has a force on it due to the external force. But the net force is going to have to be what? For an element of zero mass undergoing simple harmonic motion, the force has to be zero. If it were finite, you would have infinite acceleration. We don't have that for simple harmonic motion, right? We went through all this, remember? So the net force is going to have to vanish here. I just want to point that out. And in fact, because this is going to come up later, you'll see when we get to resonance. As an example, as a real simple example to get a physical field, consider the quasi-static limit. Okay, so now this frequency is very low. This force is going very low. What's the response going to be? You don't need to look at the wave equation. Just physically, what's the response going to be? What's the response on the left side going to be if I'm going really slowly?
Just follow it.
Yeah, but what's the waveform going to look like? Straight line.
Straight line.
Yeah, it's just going to go. It's going to look like this. Okay. It's going to be going. It's going to be going like this. What about this? The right-hand side.
Flat line.
Yes. Is there? Do you see the discontinuity in slope? Yeah. There's a discontinuity in slope. Our waveform, at some point in time, is going to look like this. Okay. So at the center point here, you can see the string is exerting a net force, transverse force. This side is not exerting any transverse force. This is exerting it. That's going to be balanced by what? The force. Okay? So that's the general situation. And I'm just pointing it out because the resonance is, of course, going to be different, as you'll see. Okay, so how do we solve this? Well, this is the course on impedance here. So and it really does make the solution easier. To typical physicists who don't work with impedance, they would just start writing down solutions to there's a solution to the wave equation here, a solution here, and they'd be taking them it would take a long time, and they would essentially be rederiving these impedances. So we've already derived them, so that's one of the big advantages. I'm just reiterating this. I've told you this before. All right, so the input impedance here, we see the sum of the two impedances. And now, as opposed to that a previous problem that we did, they're going to be different. So let's look input of forced. So the impedance going this way, this is a forced fixed string. And we know that the impedance is equal to this. Okay, now I've set what we solved for, again, we solved it for L, but I have to just replace L with L over 2. How do we get the impedance here? Well, we didn't actually directly solve for that, but we did solve for the impedance when you have a mass here. Remember that, sliding on a frictionless pole? So we can just look at that solution and set the mass equal to 0. Sounds like a quiz problem, doesn't it? So, so here's the impedance. If you look back, you'll see, and this is actually the way you want to. You will be looking at this. This really comes from the impedance translation formula. It's not exactly the same. I don't have the I's here, but that's what we're going to be using more and more of in this quarter and next. So you can look back and see this is the result of the impedance as a function of m. We just set that mass equal to 0. Nothing stops us from doing that, and now we get the impedance of a free end. So it's a tangent KL over 2, as opposed to cotangent. They're not the same, right? The boundary conditions are different here. The total input impedance is the sum of the two impedances. So here we go. And now this is a forced drive, so KFCS have no problem with this. We can use the standard procedure. Resonance, how do we define resonance? The vanishing of the reactance, right? This is purely reactive. The impedance here is purely reactive. It's purely imaginary because we have no dissipation. So we're going to have to zero this out. And now we get to this. It's kind of curious, right? Cotangent equals the tangent. The cotangent is 1 over the tangent. So this is equivalent to the tangent squared being 1. If I take the square root of that, what do I get? Trick question.
Minus plus 1.
Right, right. What's the square root of 1? Plus or minus 1. Yeah, you don't want to miss that because you would be missing half of the resonances, okay? So you need to be careful when you take the square root. And just after a while, you just don't even, some little thing goes off in your head and you just do it. So does everybody get that? Yeah, we have to, when I take the square root here, the reason I can have a minus is, all I know is that when I square this, I have to square each side, I have to get the tangent squared equals 1, and I do get it with the minus when I square that. So what do these look like? Well, you can see the first one here, pi over 4. The tangent of pi over 4 is 1. So when KL over 2 is equal to pi, that's going to give me this one. That's our first resonance. And then to get the next one, I got to advance it by pi over 2. Because that's going to give me this angle has a tangent of minus 1. So these pluses and minuses are going to alternate here. Here the tangent is equal to plus 1. For this angle right here, which is 3 pi over 4, the tangent is minus 1. You see the angle, see this angle here, it's going to have an opposite over the adjacent. It's negative because this is negative. So they just toggle back and forth here. And if you think about it, eventually we can write it this way. Here's the first one, and then we add half integral multiples of pi. So that's what I'm doing here, except for the first one. So that's why I have the n minus 1. So this is one way of doing it, and then you can bring these two together if you like into one. That's what's done right here. So we've found the resonances. To physically appreciate this, the next thing we want to do is get rid of k here. We usually find them in terms of k because that's the convenient theoretical quantity. But really what we want are wavelengths, right? So, and we usually go through that, and we also get the frequencies at the same time. So in this case, we said omega is equal to ck. That's going to give us omega. The frequencies are omega divided by 2 pi. So here's the spectrum, the frequency spectrum of the modes. And the wavelength is, of course, the speed of waves over the frequency, right? This is just velocity is distance divided by time, as I said before. So if you plug this in, the frequencies here, you get this, and you can identify that we're getting, this is what we're getting. These are the resonances. Now, what happens, where's the drive? Oh, incidentally, the resonances are infinite because we have no dissipation here. And you can, should be able to verify that. Yeah, we really don't have the waveform, but because we have no dissipation, they're going to be infinite. Yeah, we skip that. It's not, but we could get that if we wanted to. So, there's no discontinuity in slope here. What happened to the discontinuity in slope? See that here? These all have, the string is exerting no net force on the element there, on a massless element. So there's the force. We have this force. So how can that be? Well, it's because this is infinite. This is the only way it can accommodate that. It grows to infinity. It has infinite acceleration. If you like, you can imagine this thing oscillating with infinite amplitude. It's going to have infinite acceleration, which is consistent with the fact that there's a net force on a massless element. I think we can look at it that way. So this actually makes physical sense because of this, that the system is going to, the only way it can handle, it's consistent with the fact that there's a finite force on this vanishingly small element of mass, and the amplitude just grows without, it's going to have infinite amplitude. Okay, so that's it. Are there any questions? So I think lab 2 is kind of okay now, right? And I want to apologize to somebody. Sometimes when you come to my office, I'm kind of ornery. Is that a word people still use? Sometimes I'm not in a great mood, and it's because I'm, dealing with the distance learning students. Not that there's anything wrong with the distance learning students, but it's just computer, communicating over the computer and stuff. So I want to apologize. Sometimes I'm not, but I think we've got experiment 2 pretty well down, right? If anybody has any questions about that, especially the distance learning students, I haven't seen any reports yet, preliminary reports from the distance learning students, but I think everyone here is okay, right?
Yes, sir.
Some of you have to check things. Okay, good. And we have another experiment this Friday. That's waves on a string.